Andrei Shebetov's educational video. Chebyshev's bias. From 1853 to 2018. 165 years of history. Chebyshev's bias is a phenomenon known for 165 years, and extensively researched by a number of outstanding mathematicians from all over the world. It is closely related to the Generalized Riemann Hypothesis, that laid the foundation of the modern number theory. In 165 years, mathematicians, mainly British and American, managed to test Chebyshev's bias numerically for primes up to 10 to the power of 12. The main goal of my project was to expand this range 5,000 times, and to test Chebyshev's bias for 15 most biased prime number races, established theoretically by two Canadian mathematicians in 2013. I also checked all newly found zones against theoretical predictions made over the past 20 years. In addition, I plan to make all project data, for the first time, available to all mathematicians in full by contributing them to the online encyclopedia of integer sequences, and to the repository on my website. Chebyshev, who lived in the 19th century, was a brilliant Russian mathematician and is considered to be a founding father of Russian mathematics. He was honored in many ways, including an asteroid and a lunar crater named after him. Chebyshev is well known for his work in the fields of probability, statistics, mechanics, and, especially, number theory. For his outstanding contribution to the number theory, he was elected the member of Paris Academy in France and Imperial Academy of Sciences in Russia. He was also a member of the Royal Society of London, the Royal Prussian Academy of Sciences, the Royal Swedish Academy of Sciences, and many other science institutions. In 1853 he wrote a famous letter to his professor and fellow mathematician Pavel Fuss, who was a grandson of Leonhard Euler. In this letter he made an interesting observation that there are more primes that are congruent to 3 modulo 4, than primes that are congruent to 1 modulo 4. Since then this conjecture as well as its generalization has been called Chebyshev's bias. Chebyshev's conjecture was the origin for a big branch of modern number theory, namely, comparative prime number theory, as was written by Sergei Konyagin from Russia and Kevin Ford from the USA in their joint paper. Chebyshev's letter to Fuss is still cited in each and every paper in this field. Chebyshev's bias could be easily expressed through prime counting function called prime pi. In modulo 4 case, prime pi could be divided into two prime pi functions with residues 3 and 1 respectively. These functions compete with each other, and this competition is often called prime number race. Chebyshev just guessed that one of the teams always had a lead over the other. The same conjecture or Chebyshev's bias applies to other moduli and resulting prime number races. The difference in the number of primes in two competing teams is called delta. If Chebyshev was right, delta should always be positive. If we look at modulo 4 race delta, it seems to be the case for a long time. No negative delta had been known for over 100 years since Chebyshev's letter to Fuss. The first negative point was discovered only in 1957 at a prime number equal to 26,861. And the next one was located at 616,841, a way too far for a manual search. Extensive search for negative delta became possible only with the advent of computer era. Finding zones with negative delta was difficult. They were really rare and often contained just a few negative points. But even before the first negative delta was actually found, mathematicians had been sure that Chebyshev was wrong. It was theoretically proven by John Edenser Littlewood in 1914, 60 years after the Chebyshev's letter to Fuss. Littlewood proved that no matter what, there would always be zones with negative delta. So, the discovery of the first zone was expected, though somewhat belated. Despite Littlewood's theorem, negative zones for delta happened so infrequently, that in 1962 a Polish mathematician Stanislaw Knupowski and a Hungarian mathematician Paul Turon suggested that Chebyshev's guess should be valid asymptotically, or, in other words, in infinity. After the discovery of the first zone in 1957 and appearance of Knupowski-Turon conjecture, there had been extensive search for new zones with negative delta for 40 years up to 1996. Some great minds of that time like John Leach and Derek Lemmer participated in the search. But the major contribution was made by two American mathematicians Carter Bayes and Richard Hudson, who managed to test the range up to 10 to the power of 12 for the most interesting moduli. They were successful in finding new zones for moduli 3, 4, and 8, but did not succeed much for the moduli 12 and 24. The efforts of Bayes and Hudson became especially important, as two American mathematicians, Michael Rubinstein and Peter Sarnak, made a real breakthrough in 1994. They proved that if the generalized Riemann hypothesis was true, then the Knupowski-Turon conjecture should be false. This was also independently proven by a Polish mathematician Jerzy Koczorowski. Bayes and Hudson's data clearly indicated that Knupowski-Turon conjecture was false. The connection and resulting switch to generalized Riemann hypothesis was important, as it allowed to replace the sum over primes in arithmetic progression by the sum over zeros of corresponding Dirichlet L-function. As a result, some periodicity appeared in math formulas. Periodicity meant that negative zones should appear from time to time. In addition, Rubinstein and Sarnak introduced the notion of logarithmic density and proved its existence for general prime number races. This became extremely important to determine what the most unfair prime number races are. Logarithmic density simply meant the probability that one team would prevail over the other in the corresponding race. They also calculated logarithmic density for various races, including modulo 4 race, and came to the conclusion that Chebyshev was right 99.59% of the time. Bayes and Hudson spent 25 years investigating Chebyshev's bias, but why did not they move beyond 10 to the power of 12 range? The answer is very simple: this was beyond the technical capabilities of that time. There were no fast and reliable prime number generators for big primes, and computers were not as powerful and reliable as nowadays. As technical limitations persisted, Bayes and Hudson concentrated on theoretical explanation of Chebyshev's bias, and made a number of important predictions for new zones. Some of them below 5 times 10 to the power of 15 were checked in this project. Several zones were predicted beyond the upper limit of the project, but actually happened much lower than expected. Using Rubinstein's and Sarnak's idea of logarithmic densities, two Canadian mathematicians, Furilli and Martin, in 2013, calculated and published logarithmic densities for 120 most biased, or, as they called them, most unfair prime number races. I selected top 15 of them for this project. When Furilli and Martin published their article in 2013, there had been negative zones known for only 4 races from their top 15 list. Remember that each found negative zone supported the validity of generalized Riemann hypothesis. So, finding them was very important. To achieve project goals, I developed 2 programs in C++. The first one allowed to test any modulo race with 2 selected residues, whereas the second one tested only moduli below 30, but for all possible combinations of residues. Both programs used a fast real-time prime number generator called PrimeSieve. These programs allowed to test Chebyshev's bias up to 1.8 times 10 to the power of 19, much higher than the upper bound of this project. In addition, a control program was written in C# that worked with a large prime number database up to 10 to the power of 12. This was about the same way as used by Bayes and Hudson 20 years before. The control program was necessary to verify independently with different algorithms the correct work of the main programs. After my software was tested and confirmed with previously known numbers below 10 to the power of 12, it was launched on 5 remote Microsoft Azure servers to expand the known range 5,000 times. The project took about a month to get from the known Bayes and Hudson results, initially, to 10 to the power of 15, and, then 3 more months, to expand it further to 5 times 10 to the power of 15. Now you could see a short demonstration of the main program operation. Upon authorization, you need to enter the tested modulus and main residue, the start point and initial data, if any, the end of your tested range and the frequency of output to control program work and its % of completion. All results for all pairs of residues for all found negative zones are automatically written into several files on the computer hard disk. If interrupted, the program could start from the last saved prime number and associated data points. Coming to the results, let's compare the status of negative zone search for most biased prime number races in 2013, when Furilli and Martin published their list, and after the completion of my project. If in 2013 out of top 15 races, negative zones were known for only 4, now they are known for 9 races. Only top 5 and number 7, 6 in total, remain unknown. Remember that these zones need to be found to support the validity of generalized Riemann hypothesis. Summarizing, I found 25 new zones including 4 first-ever zones for 4 most biased prime number races out of top 15. I also discovered that though theoretical models predicted big and wide zones relatively well, in many cases, they failed to predict small and narrow zones, that happened more often than mathematicians thought. For example, for 1 versus 5 modulo 8 case, 3 small and narrow unexpected zones occurred before 2 large ones that were correctly predicted by theoretical models. This definitely requires some theoretical explanation. All found zones are included in 18 sequences, contributed to the online encyclopedia of integer sequences. For the first time, they became available in full and unabridged form, to all mathematicians working in a prime number theory field. These data were updated from time to time as our program provided new data. In addition to the online encyclopedia of integer sequences, all project data are available at the data repository on my website, math101.guru. Let's make some conclusions. First, I managed to expand successfully 5,000 times, to 5 times 10 to the power of 15, the range previously tested by mathematicians. Second, I tested 15 most biased prime number races established theoretically in 2013. Third, I found 25 new zones for 9 most biased prime number races, including the first ever zones for 4 races. This is significant progress in Chebyshev's bias area. Fourth, I confirmed numerically that theoretical models, developed over the past 20 years, predict big and wide zones relatively well, but fail to predict small and narrow zones that occur more frequently than assumed. Therefore, these models need review and revision to accommodate project results. This project numerical results are objective, whereas theoretical models are based on some presumptions, conjectures, and hypotheses. Finally, and most importantly, the results of my project support the validity of generalized Riemann hypothesis. This hypothesis, if ever proven, will have a big impact on a number of practical areas such as cryptography, coding theory, random number generators and quantum computing. Thanks a lot for your attention and, please, Visit my Math101.guru website.